This lesson is on solving systems of equations by Laplace transform. For some reason or other, I can't find my computer.
Over here.
Oh, where?
Over here.
Oh, I think that's it. Oh, I bumped my knee. Oh.
Poor baby.
Okay, well, I'm all right now. Anyway, how do you solve a system of equations by Laplace transform? I thought I would demonstrate by some examples. So after we transform the system of differential equations into the algebra domain, we can use algebraic operations to solve the algebraic problem. Then find the inverse transforms as the solutions to find the solution of the system. Here's an example. We got x prime plus y equals sine of t, y prime minus z equals e to the t, and z prime plus x plus y equals 1. With initial condition x is 0 is 0, y of 0 is 1, and z of 0 is 1. So, looking at the first equation, the transform of this is s times x minus 0 times s, so we'll just say s times x, and then plus the transform of y, we'll just call it y, capital Y, and the transform of sine of t, you should know that one, 1 over s squared plus 1. So there's the transform of the first equation. The second equation would be s times y minus this 1, and then minus z is just minus z, transform of z, equals 1. Well, the transform of 1 is, I'm sorry, I'm in the wrong one. I'm in the second equation. Equals e to the t. The transform of e to the t is, that's e to the 1t, so 1 over s minus 1. So there is the transform of the second equation. Here's the transform of the third. Z prime, which is going to be sz minus 1, this 1, plus transform of x plus transform of y equals the transform of 1, which is just 1 over s. So adding the 1 that came up here and here to both sides and rewriting the right side for these, all of these, gives us sx plus y equals 1 over s plus 1. I add the 1 to both sides, then the common denominator would be s minus 1, so the 1 is s minus 1 over s minus 1. I think you can see why that gives us sy minus z equals s over s minus 1. And when we add the 1 to both sides for this one, that's 1 over s plus 1, common denominator of s, so it's s plus 1 over s. So sz plus x plus y equals s plus 1 over s. Now algebraically, we want to solve for x, y, and z. So if we add s times the middle equation to the bottom equation, you can see that my sz's would then cancel. And then this third equation and the top equation will only have two variables in it, x and s. So this is the first one. This would be the next one. When we add s times y to this one, we get s plus 1 times y squared. Well, we don't have any x's to add to this 1x, so we got 1x. And that is equal to s times this, so s squared over s minus 1 added to the s plus 1 over s we already had there. And if you find a common denominator, you can see that it comes out to be s cubed plus s squared minus 1 over s minus 1, if you just do the algebra on that. So now what we want to do is use elimination by adding negative s squared plus 1 to this equation and adding it to the equation on the bottom. So negative s squared plus 1 times s is going to be negative of s cubed plus s minus 1 times x. This is the s negative x s cubed minus s, and then plus this 1, but I factored out the negative, so I think you can see how that works algebraically. Of course, the y part cancels out, that's why we did it. When you multiply this by negative s squared plus 1, you just get negative 1, which is here. And this part was added to, so it's this whole thing right here. Now, common denominator, and simplifying this with a minus 1, if you did the algebra on that, we would get minus 1 is minus s squared minus s. And so the minus s squared takes care of this, and the minus, well, the minus negative s makes this into a positive s. So we wind up with s cubed plus s minus 1 over s times s minus 1. Check the algebra on that if you don't believe me. So now when we divide both sides by negative s cubed plus s minus 1, we do wind up with x equals negative 1 over s times s minus 1. Partial fraction decomposition would make that 1 over s minus 1 over s minus 1. And so we got our x is the inverse transform of 1 over s minus the inverse transform of 1 over s minus 1 due to the linearity of transforms and inverse transforms. So x of t is 1 minus e to the t, 1 being the inverse transform of this, e to the t the inverse transform of this. Now we want to find y of t for the system, so let's see how that goes. If we started with what we wound up with after that little trick where we multiplied, where did we do that? Multiplied this equation by s and added to this one to eliminate the z. We'll go back to that position, but now this time we'd like to eliminate x. So we're going to add negative s times this equation to this equation, and so I think you can see that the s's, the sx's will then eliminate. One will be positive, one will be negative. Negative s times this added to this y would give us negative s cubed minus s plus 1 times that y equals this side with a negative in front of it. See that? Because it's negative s added to this. So, and then add to the side we had there in the first place. So now algebraically these two things need to combine, and you'll have to trust me on the algebra, but I did it, and it did wind up being s to the fifth plus s to the fourth plus s to the third minus s over s minus 1 times s squared plus 1. And of course the left side I did factor out the negative, but still these negatives both cancel, and so we get this situation, s cubed plus s minus 1 times y equals this horrible partial fraction over here. But then we need to divide by the s cubed plus s minus 1, and now we have a sincere partial fractions problem. However, if you factor out the s from this, you might be able to actually discern that it's s times s plus 1 times s cubed plus s minus 1. If you struggle with that, what I did was factor it over here and then see that s equals negative 1 is a root of this, because this would be positive and this would be positive and this would be negative, so you get 0. So if s equals negative 1 is a root, then s plus 1 is a factor. So I actually used the rational root theorem from pre-calculus to do that. Well, why that was handy was because what was left over after I factored out that was s cubed minus s minus 1, and that canceled with this. And so we got y equal to s times s plus 1 over s minus 1 times s squared plus 1. Partial fraction decomposition for that, just trust me, is 1 over s minus 1 plus 1 over s squared plus 1, and you can work that out. But either way, then the inverse transform of this, of course, is e to the t, so y of t is e to the t. The inverse transform of this is sine of t, so there we've got our y. Now, we can finish solving this equation for z since we know y. So z equals, now be careful the way I mess with the signs on that, but z equals s times y minus s over s minus 1. And s times y, remember this was our y. Recall that came from here, right? So that's s times this y minus s over s minus 1. Well, that's not too terrible bad. So finding the LCD, which is not too hard, this just needs an extra s squared plus 1 in it, so we wind up with s squared times s plus 1, which we got from this s times this s. So and then the common denominator, we need an extra s squared plus 1 in the numerator, so now we got a common denominator and we can do our subtraction, And if you do that, you notice this is going to be s cubed plus s squared. That's going to be minus s cubed minus s. So we get s squared minus s over a common denominator. And simplifying that, the s minus 1's cancel. It's just s over s squared plus 1. So it's easy to recognize that z is cosine of t. So we have our solution. X of t is 1 minus e to the t, y of t is e to the t plus sine of t. Z equals cosine of t. And you know what that was? That was rough.